Welcome. Today, we're providing a definitive technical reference on Snowflake Virtual Warehouses. For any architect or platform leader, mastering compute is really the single most critical lever you have for optimizing both performance and cost. Think of this as your architectural guide to achieving that mastery.
So the central idea is this. Any successful Snowflake implementation is truly defined by its compute strategy. How you choose to select, size, configure, and ultimately govern your virtual warehouses, well, that's what's going to directly determine the efficiency and the economic viability of your entire data platform.
We've structured this deep dive for clarity. First, we'll start with Snowflake's foundational architecture, and then we'll explore the modern toolkit of warehouse engines available today. From there, we'll get into the economics of sizing and cost, cover some advanced configurations, and finally, we'll pull it all together into a practical selection framework backed by real-world architectural patterns.
Okay, so it all begins with Snowflake's core principle, the complete and independent separation of storage and compute. This is really the architectural hallmark that enables the platform's incredible elasticity and concurrency.
Snowflake's architecture, as you know, has three distinct layers. At the bottom, the storage layer holds all your data in centralized compressed micro-partitions. Up top, the cloud services layer acts as the brain, managing everything from optimization to transactions and security. And right in the middle, you have the compute layer, which is populated by these independent virtual warehouses. Now, these warehouses are ephemeral, which means they can spin up on demand, access the data they need, and then be scaled or suspended without any contention. This is what truly separates compute from storage.
Now, this architecture has a really direct performance implication. See, each warehouse maintains its own local SSD data cache. A warm warehouse, one that's been running, serves data right from this super-fast cache. But suspending the warehouse clears it. So what happens? The very first query after it resumes creates what we call a cold start, because it has to read directly from the slower, remote object storage. This is an absolutely critical factor to consider for any latency-sensitive workload.
All right, with that foundation in mind, let's take a look at the compute engines themselves. Snowflake gives you a pretty specialized toolkit of warehouse types, and each one is engineered for a very specific workload. Selecting the wrong tool for the job is a primary driver of both performance issues and cost overruns. So the workhorse is the standard warehouse, and it now comes in two generations. Gen 1 is your traditional x86-based engine, but Gen 2, which runs on AWS Graviton3 ARM processors, offers a really significant performance uplift. We're talking about 2.1 times faster for core analytics workloads. It's available up to a 4XL, but it does require an explicit configuration change to enable it.
One of the best parts is just how simple the upgrade path is. Migrating to that higher performance Gen 2 engine is just a single SQL command. You just alter the warehouse and set the resource constraint parameter to standard Gen 2. That's it.
Next up in our toolkit is the Snowpark-Optimized warehouse. And its primary benefit is, well, it's straightforward and incredibly powerful. It provides 16 times more memory per node than a standard warehouse of the exact same t-shirt size. This is purpose-built for those really memory-intensive, single-node workloads like machine learning.
And critically, just like with Gen 2, these warehouses are configured using that same resource constraint parameter. This lets you control not only the memory multiplier from a baseline 1x all the way up to an extreme 64x, but also the underlying CPU architecture. And this is essential for making sure you have compatibility with Python libraries that might have x86-specific dependencies, like older builds of TensorFlow, for instance.
The newest engine in the toolkit is the interactive warehouse. It's specifically engineered to solve that cold start problem we talked about, but for workloads that absolutely demand sub-second latency. Think live, customer-facing dashboards or embedded analytics APIs. Its core principle is an always-warm architecture, which, by design, just eliminates that resume latency completely.
And finally, any standard warehouse can be configured for multi-cluster to handle concurrency. This isn't a separate type, it's a scaling configuration. The scaling policy is what dictates its behavior. The standard policy is all about performance. It adds a new cluster very quickly when queries start to queue up. The economy policy, on the other hand, prioritizes cost. It'll wait about 6 minutes before scaling out, which means it tolerates some queuing to save credits. And for total predictability, maximized mode just runs all of your configured clusters continuously.
All right, let's shift gears and focus on the economics of all this. Understanding that direct relationship between warehouse size, credit consumption, and cost is really fundamental to building a sustainable platform. The sizing model is refreshingly linear and predictable. Every time you step up in t-shirt size, say from an X small to a 6X large, you are doubling the number of compute nodes in that cluster. And that in turn doubles both the compute resources and your credit consumption per hour. So an X-large warehouse, for example, is going to consume 16 credits for every hour it's running.
This chart really drives home the exponential nature of that cost growth. As you scale up vertically, that per-hour cost accelerates pretty dramatically. It really reinforces the importance of right sizing. You know, before you jump from an extra large to a 2x large, an architect really has to ask, could a multi-cluster configuration at the smaller size achieve the same throughput more economically?
So how do you actually know if you've sized it correctly? Well, you have to use diagnostic queries against the account usage schema. A key indicator, a real red flag, of an under-provisioned warehouse is disk spillage. When a query runs out of memory, it starts spilling data to local or even remote disk, and that just kills performance. This query lets you pinpoint exactly which warehouses are spilling and by how much, signaling that you probably need to increase their size.
Okay, so beyond just the type and size, there's a whole suite of advanced parameters that give architects precision control over warehouse behavior. This is where you can really fine-tune for performance, cost, and governance.
These properties give you that fine-grained control. Auto-suspend is your main cost-saving lever for idle warehouses. Scaling policy, as we discussed, manages that trade-off between performance and cost for concurrent jobs. Enable query acceleration is there to handle those unexpected peak loads, while a resource monitor provides a hard budgetary ceiling. Mastering these is really key to operational excellence.
So let's properly define the Query Acceleration Service, or QAS. Think of it as a serverless compute fleet that assists your standard warehouse. When QAS spots an outlier query, one that's way too large for the typical workload, it offloads parts of that query's execution. And here's the crucial point. This allows you to size your warehouse for the 95th percentile workload and let QAS handle those unpredictable peaks. It prevents queuing, but without the cost of running a permanently larger warehouse.
And for governance, we have resource monitors. These are the primary tool for enforcing your budgets. This SQL command here shows how to create a monitor with a monthly credit quota. And you can define multiple triggers. For example, you can notify it 90% consumption and then have it suspend the associated warehouses immediately once that quota is fully exhausted. This prevents any possibility of budget overruns.
So this brings us to the central architectural question, right? With this whole rich toolkit of warehouse types, scaling policies, and advanced configurations, how do you systematically choose the right combination for any given workload?
Well, the answer lies in a structured decision framework. We can take all of this information and synthesize it into a repeatable process that guides architects to the optimal compute configuration every single time.
And here it is, the decision tree. We just evaluate the workload's core characteristics one by one. First, you ask, is it memory intensive, like ML training? If yes, you choose Snowpark-Optimized. If not, does it need that sub-second API latency? If yes, you go with an interactive warehouse. You just follow this logic, addressing concurrency, hardware, and outliers, and you can systematically route every workload to its ideal compute engine.
And this table translates that framework into some concrete recommendations for common enterprise workloads. So for production dbt runs, a large or X-large standard Gen 2 warehouse is usually the sweet spot. For those high concurrency BI tools, a medium Gen 2 warehouse with multi-cluster and QAS enabled is the standard pattern. This is how we map that theory directly to practice.
So now let's look at the framework in action. We'll move from those prescriptive patterns to some real-world enterprise architectures where these principles have been successfully applied.
Our first use case is from financial services. A platform was seeing a lot of contention between fast, operational master data management lookups and these long-running analytical queries. The solution? Workload isolation. They created two separate, purpose-built warehouses, a small, always-on warehouse for the MDM lookups and a large, auto-suspending Gen 2 warehouse for analytics. This completely prevents the long queries from ever blocking the critical operational ones.
Now in retail, predictable peak events like Black Friday demand a proactive scaling strategy. So instead of just reacting to performance problems, this pattern uses a scheduled Snowflake task. The task just executes an alter warehouse command automatically before the peak event hits, increasing the minimum and maximum cluster count. And then a second task scales the warehouse back down after the event, ensuring top performance during that critical window while still controlling cost.
And in healthcare, this pattern enables secure end-to-end machine learning. By creating a Snowpark-Optimized warehouse with an x86 constraint, an entire patient risk modeling pipeline, from feature engineering all the way to model training, can execute entirely inside Snowflake's governance boundary. This completely eliminates the security risk and complexity of moving sensitive patient data out to an external training environment.
So, as we wrap up, let's distill all of this technical detail into the key strategic principles that really should guide every platform leader and architect.
Really, 4 principles form the foundation of a mature compute strategy. First, absolute workload isolation. Second, continuous right-sizing based on the real data you see in the account usage schema. Third, proactive cost governance. Use resource monitors as a default, not an afterthought. And fourth, a strategy of progressive modernization, adopting new capabilities like Gen 2 and QAS where they deliver clear value.
You see, the goal isn't just to deploy the largest warehouse, it's to deploy the right one. A platform leader's real responsibility is to ensure precision and control, that every single warehouse is purpose-built, that it's right-sized based on observed behavior, and that it's protected by a non-negotiable governance layer.
So we'll end with a question for you to consider. Is your current warehouse architecture intentionally designed to serve your workloads? Or are your workloads, and by extension your business outcomes, being compromised by a generic or an outdated compute architecture? For a much deeper analysis, you can download the full technical white paper.